All right, so we're diving into some CCNA material today. Looks like you're really trying to get a handle on internet working
Yeah, it's definitely a field with a lot to learn.
and a lot of acronyms. Right, it's like alphabet soup sometimes.
It's true, there's a lot to learn,
Hmm.
but we're gonna break it down, make it make sense.
Exactly. Think of this deep dive as your like crash course, cutting through the jargon.
To the essentials you need for that CCNA exam.
Right, like the OSI model.
Ah, yes, the OSI model stands for Open Systems Interconnection. It's divided into 7 layers,
7 layers, okay.
each with a specific function. You can think of it kind of like a building
Okay.
with different floors dedicated to different tasks.
So like a building, gotta have that foundation.
Right, that would be the physical layer. Layer 1. This is where we deal with the nuts and bolts.
The nuts and bolts.
Okay.
Yeah.
The cables, connectors, the electrical signals that carry the data.
So like understanding bandwidth is crucial here. What exactly does bandwidth mean?
Bandwidth. It's essentially the capacity of a network connection, the amount of data that can be transmitted per second.
Per second. Okay.
Think of it like a highway.
Okay.
The wider the highway, the more cars can travel on it at the same time.
Right.
More bandwidth means faster data transfer.
Makes sense. So how does the physical layer differentiate between things like baseband and broadband transmission?
Baseband transmission, it sends one signal at a time,
Uh-huh.
using the entire bandwidth. Imagine a single train track. Only one train can travel at a time.
Gotcha.
Broadband, on the other hand, allows multiple signals to be transmitted simultaneously, like having multiple train tracks running in parallel.
Oh, okay. So that's why cable internet is generally faster than dial-up.
Exactly. Cable internet uses broadband, dial-up uses baseband.
Ah, that makes a lot more sense now. So are there other key concepts within the physical layer that are important for the CCNA exam?
Absolutely. You'll need to know about different cabling types,
Yeah.
like twisted pair and fiber optic, as well as their characteristics and uses. Additionally, understanding the different types of connectors used in networking is important.
Okay, so the physical layer is all about like laying the groundwork,
Right.
the physical infrastructure of the network. So let's move up to the next floor,
Okay.
the data link layer.
The data link layer, layer 2. We focus on getting data to the right destination on a local network.
Local network. Okay.
This involves things like MSC addresses,
Okay.
which are unique identifiers for each device.
Like a device's what, serial number or something?
Kind of, yeah. And switching, which directs data between different devices on the network.
So if we imagine data as packages being delivered, the data link layer is like the mailroom, sorting and labeling the packages for local delivery.
Yeah, that's a good way to think about it.
Okay.
A key technology at this layer is Ethernet,
Ethernet.
which defines the rules for communication on a local network. You might already be familiar with this term,
Right, Ethernet.
as Ethernet is the standard used for most wired networks.
So what are some of the key things to know about Ethernet for the CCNA exam?
Understanding how Ethernet handles data collisions is important.
Data collisions.
Yeah, imagine multiple devices trying to send data at the same time. It could create a traffic jam on the network.
Oh, okay.
Ethernet uses a mechanism called CSMAS-MD, or Carrier Sense Multiple Access with Collision Detection, to prevent these collisions and ensure data integrity.
So it's got like built-in traffic management.
Exactly.
That's pretty cool. Are there any other important concepts at the data link layer?
Yes. Another important concept is VLANs,
VLANs.
or virtual LANs.
Okay.
These allow you to segment your network logically.
Segment the network.
Yeah, separating devices into different broadcast domains, even if they're physically connected to the same switch.
Okay, why would you want to do that? Segment a network.
Well, network segmentation with VLANs, it offers several benefits,
Okay.
including improved security and network performance.
Yeah.
For example, you can separate your sensitive financial data from your guest Wi-Fi network, or group devices together based on their function, like creating separate VLANs for voice and data traffic.
Right. To keep things running smoothly and securely.
Exactly.
So we've got the physical layer for the foundation, the data link layer for local delivery, and now we're moving up to the network layer.
The network layer, layer 3.
What's happening up on this floor?
It's all about getting data to its destination across different networks.
It's across different networks, okay.
This is where IP addresses and routing come into play.
IP addresses, routing.
IP addresses are like the addresses on those packages we talked about earlier, telling the network where the data needs to go.
Right.
Routing is the process of determining the best path for data to travel across different networks to reach its destination.
So if the data link layer is like the local mailroom, the network layer is like the postal service.
Precisely. The network layer is responsible for internetworking,
Internetworking.
connecting different networks together, enabling communication between devices all over the world.
Wow, that sounds pretty complex.
It can be.
Are there different ways to route data?
Yes, there are. One way is through static routing,
Static routing.
where network administrators manually configure routes between networks.
Okay.
This can be manageable for smaller networks, but it becomes difficult to scale as the network grows.
Right. So what do you do then?
That's where dynamic routing protocols come in.
Dynamic routing protocols. Okay.
Dynamic routing protocols allow routers, the devices that forward data between networks, to learn about the network topology and automatically adjust routes based on changes or conditions. Think of it like GPS for your data,
Okay. GPS for data.
constantly recalculating the best route based on traffic and road closures.
That's a fantastic analogy. So are there specific dynamic routing protocols that are important for the CCNA exam?
Absolutely. You'll need to know about protocols like RIP, OSPF, and EIGRP. These are all different algorithms that routers use to exchange routing information and determine the best paths for data.
Okay.
Understanding how these protocols work and how to configure them is essential for managing and troubleshooting complex networks.
Wow. That's a lot to take in about the network layer, but I'm starting to see how it all fits together.
Yeah, it's all connected.
We've gone from the physical connections to local area networks to connecting different networks across the globe. It's like building a roadmap of the internet.
Exactly, layer by layer.
And we've only just begun to explore the world of internetworking.
We've got a long way to go.
Okay, I'm ready for more. But before we move on, let's take a look at some of those specific CCNA terms. From the materials you sent, there are a lot of acronyms in there, and I bet some of our listeners are eager to decode them.
Yeah, let's tackle some of those acronyms. You're right, there are a lot of acronyms to unpack. In the CCNA curriculum, let's tackle some of the more common ones. How about we start with access lists? Have you come across that term yet?
Access lists, yeah, I've seen that one. I know they have something to do with security, but I'm a little fuzzy on the details.
Access lists are essentially sets of rules that control which devices or types of traffic are allowed to access
Right.
or leave a network. They act like virtual security guards,
Okay,
filtering traffic based on specific criteria.
got it.
For example, you can use an access list to block traffic from a particular IP address, or to allow only certain types of traffic, like web traffic, to pass through a router.
So they're like customized filters for your network.
Exactly, letting you control what comes in and what goes out.
Right. That makes sense from a security standpoint. What about administrative distance? I remember seeing that one too, and it sounded a little intimidating.
Administrative distance. It's actually a pretty simple concept.
Yeah.
It's a measure of the trustworthiness of different routing sources.
Trustworthiness, okay.
Routers use administrative distance to determine which routing information to prioritize
Okay.
when they have multiple sources for the same route.
So if a router gets conflicting information about how to reach a destination, administrative distance helps it decide which source to trust more.
Exactly. It's like when you're asking for directions, you're more likely to trust a map app than a random person on the street.
Right.
Administrative distance assigns a numerical value to different routing sources, with lower values indicating higher trustworthiness.
So the lower the administrative distance, the more reliable the source. Got it. Let's see, what else is on our list? ARP Address Resolution Protocol. Now that one rings a bell. It has something to do with embassy addresses, right?
You are right on the money.
Yeah.
ARP is a protocol that helps devices on a local network find each other's MAC addresses
Okay.
when they only know each other's IP addresses.
Okay, remind me again, what's an MC address?
A MAC address, or Media Access Control Address, is a unique hardware identifier assigned to every network interface card, or NIC, in a device. Think of it like a fingerprint
Okay.
for your network device.
So if a device knows the IP address of another device, but needs its MAC address to send data, it uses ARP to ask, hey, who has this IP address? What's your MAC address?
That's a great way to put it.
Okay.
ARP is essential for communication on a local network.
Right.
Because data is ultimately transmitted.
Right.
Using MAC addresses at the data link layer.
ARP, the MAC address matchmaker.
I like it.
Okay, what about DHCP? That one always sounded a bit complicated to me.
DHCP, or Dynamic Host Configuration Protocol. It's actually pretty straightforward.
Okay.
It's a protocol that automatically assigns IP addresses to devices on a network. Without DHCP, you'd have to manually configure the IP address for every device on your network, which would be a huge hassle.
Right, so DHCP is like a network butler.
Exactly. Taking care of all the IP address assignments behind the scenes. When a device connects to a network, it sends out a DHCP request, and a DHCP server assigns an IP address from a pool of available addresses. This makes network administration much easier, and ensures that devices get unique IP addresses.
DHCP, the automated IP address assigner. That's definitely a time saver. Okay, let's see. What else is on our acronym hit list? Oh, NAT. Network Address Translation. Now, that's one I've heard a lot about, but I'm not sure I fully understand it.
NAT. It's a crucial technology that allows multiple devices on a private network to share a single public IP address. When communicating with devices on the internet, it acts as a middleman, translating between private IP addresses used within your home or office network and the public IP address assigned by your internet service provider.
So it's like a translator.
That's a great analogy.
Okay.
NAT is essential for conserving public IP addresses.
Okay.
As there are a limited number of them available. It also enhances security by hiding the internal IP addresses of devices on your private network from the outside world.
So NAT, the IP address, conservationist, and security guard all rolled into one. I'm starting to appreciate how all these different protocols and technologies work together to make the internet function.
Right.
It's like a complex but beautifully orchestrated symphony.
It really is, and we've only just scratched the surface. There's a whole world of networking concepts to explore, but I think it's important to remember that it's not just about memorizing acronyms and definitions.
Right.
It's about understanding how these concepts work in practice and how they can be used to build and manage real-world networks.
You're absolutely right. So let's keep digging into these CCNA materials and see what other insights we can uncover. What about ATM? That one sounds more like something I'd find at a bank than in a networking textbook.
ATM, which stands for Asynchronous Transfer Mode, is a high-speed networking technology that was designed to handle various types of traffic, including voice, video, and data, all in the same network.
So it's like a multi-lane highway for data, with different lanes for different kinds of traffic?
Exactly. ATM uses fixed-size cells to transmit data, which makes it very efficient for real-time applications like video conferencing, where delays can be disruptive.
Interesting. So ATM is all about speed and efficiency. What about boot ROM? I think I've seen that term flashing on my router before.
Boot ROM is a special type of memory in a router that contains the instructions it needs to start up. Think of it like the router's brain, telling it what to do when it first powers on. It loads the router's operating system, iOS, into memory, allowing it to function.
So it's like the router's BIOS.
Exactly. Without the boot ROM, the router wouldn't know how to start itself up, or what software to run.
Root ROM, the router's brain. Got it.
What about bridges? Are those like physical bridges connecting different parts of a network?
Bridges are actually more like intelligent connectors that operate at the data link layer. They connect different network segments and filter traffic based on MAC addresses, helping to improve network performance and security.
How so?
By segmenting traffic. So they're like traffic directors, making sure data gets to the right place.
Precisely. They can also help to isolate problems on a network. By preventing traffic from one segment from flooding another.
Okay, bridges network traffic directors. Got it. What about broadcasts? I think I've heard that term in relation to Wi-Fi.
Broadcasts are a type of network communication where a message is sent to all devices on a network segment. They're useful for things like discovering devices on a network or sending out alerts.
So it's like shouting in a crowded room.
That's a good analogy. But just like shouting in a crowded room, broadcasts can create a lot of noise. If they're not managed properly. Too many broadcasts can lead to network congestion, slowing things down.
Okay, broadcasts use them sparingly. What's next on our list of CCNA essentials?
Let's talk about buffers.
Buffers, like the loading symbol I see when I'm streaming a video.
Similar concept. In networking, a buffer is a temporary storage area for data packets. Routers and switches use buffers to manage traffic flow and prevent data loss. If a router receives a burst of data packets, faster than it can process them, it can temporarily store them in a buffer until it can catch up.
So if a router is like a busy intersection, a buffer is like a holding area for cars waiting to go through.
Exactly. Buffers are essential for smooth network operation, especially when dealing with high-volume traffic. Without buffers, data packets could be dropped, leading to slowdowns and interruptions.
Buffers data traffic shock absorbers. Makes sense. What about bus topology? Is that like a network where all the devices are riding on the same bus?
In a way, a bus topology is a type of network layout where all devices are connected to a single cable, called a bus. It's a simple and inexpensive topology, but it can be vulnerable to failures,
How so?
since a break in the cable can disrupt the entire network.
So it's like a single track railway line. If there's a problem on the track, everything comes to a halt.
Exactly. That's why bus topologies are not as common as they once were. More robust topologies, like star and ring topologies, offer better fault tolerance.
Okay, bus topology, simple but risky. What about checksum? Is that like a math problem for data packets?
Checksums, they're a type of error detection mechanism used to ensure the data packets haven't been corrupted during transmission.
So it's like a safety check?
Exactly, to make sure the data arrived intact.
Okay.
The sender calculates a checksum value based on the contents of a packet, and the receiver recalculates the checksum upon receipt. If the values match, the packet is considered valid. If they don't match, it means the data has been corrupted somewhere along the way, and the packet needs to be retransmitted.
Checksums. Keeping data corruption in check. Got it. What about CIDR?
CIDR, or classless interdomain routing, is a method for allocating and routing IP addresses that is more flexible and efficient than traditional class-based routing.
Okay, I remember you mentioning classless routing earlier. Can you remind me what that means?
Sure. Classless routing allows for more efficient use of IP addresses by ignoring the traditional class boundaries that used to define how IP addresses were assigned. It's a key concept for understanding how the internet works today.
So CIDR is like a smarter way to manage IP addresses in a world with like billions of devices online.
Exactly. It helps to conserve IP addresses and makes routing more efficient. It's a foundational concept for modern internet routing.
CIDR, IP address management for the modern age.
Yeah.
Okay, I'm starting to feel like a CCNA expert already, but I know there's still more to come. Let's keep going.
You're doing great. We're making steady progress through this alphabet soup of networking terms. And the more you understand, the better prepared you'll be for that CCNA exam. What's next on our list?
Let's see. How about configuration register? I think I've seen that term in the Cisco documentation.
The configuration register is a special setting on a Cisco router that controls how it boots up and what configuration it loads. It's like a set of instructions. That tells the router where to find its operating system and configuration files.
So it's like the router's boot menu.
Exactly. The configuration register can be modified to change the router's boot behavior,
Okay.
which can be useful for troubleshooting or upgrading the iOS.
Configuration register, the router's boot menu. Okay, that makes sense. What about congestion? Is that like rush hour on the internet?
Network congestion occurs when there's too much traffic trying to use the same network resources, leading to slowdowns and delays. It's like a traffic jam on the information superhighway.
So it's like when everyone's trying to stream Netflix at the same time and the internet grinds to a halt.
Exactly. Network congestion can be caused by various factors, including too many devices trying to access the network at the same time, limited bandwidth, or hardware failures.
Sounds like a nightmare. How do you prevent network congestion?
There are various techniques for managing congestion, including quality of service, or QoS mechanisms, traffic shaping, and load balancing.
Okay.
These techniques help prioritize important traffic and distribute it efficiently across the network.
So it's like having traffic lights and alternate routes on the internet.
That's a good way to think about it. Managing congestion is a crucial part of network administration.
Congestion, the internet's rush hour. Okay, let's keep moving through our glossary. What about connections? Seems like a pretty basic term, but I bet there's more to it than meets the eye.
In networking, a connection refers to a logical or physical link between two devices that allows them to communicate.
So it could be a physical cable connecting two devices, or it could be a wireless connection like Wi-Fi.
Exactly. Connections can be established at different layers of the OSI model, and they can be either permanent or temporary.
So a wired Ethernet connection is a physical connection, while a VPN connection is a logical connection.
Exactly. Understanding the different types of connections and how they're established is fundamental to networking.
Connections, the lifelines of communication. Okay, I'm following you. What about convergence? That sounds a bit like a sci-fi concept.
In networking, convergence refers to the process of multiple routing protocols, or devices, agreeing on the best paths for data to travel. It's important for ensuring that data gets to its destination quickly and reliably,
Okay.
even if there are network changes or failures.
So it's like all the routers on the network coming to a consensus on the most efficient route.
Precisely. Convergence is essential for network stability and efficiency.
Convergence routers uniting for efficient data delivery. Okay, I'm ready for more. What about CSU-DSU? That one's a real mouthful.
CSU-DSU stands for Channel Service Unit Data Service Unit. It's a type of device that's used to connect a router
Okay.
or other data terminal equipment, or DTE, to a digital circuit, like a T1 or E1 line.
So it's like a translator between my router and the telecom provider's network.
Exactly. The CSU-DSU handles the physical interface and signaling requirements for the digital circuit, ensuring that data is transmitted correctly.
CSU-DSU, the digital circuit whisperer. Makes sense. What about cut-through switching? Does that mean data packets are literally cutting through the switch?
Cut-through switching is a type of packet forwarding technique used by some switches to improve performance. Instead of waiting for the entire packet to arrive before forwarding it, a cut-through switch begins forwarding the packet as soon as it reads the destination address.
So it's like sending a letter express mail.
A good analogy. Cut-through switching can significantly reduce latency, especially for small packets.
Cut-through switching, express delivery for data packets. I love it. Okay, I'm feeling pretty good about our glossary progress. We've covered a lot of ground, but I know there are still a few more terms to tackle. Ready to keep going?
Do it.
Absolutely. Let's keep going with this CCNA glossary. We still got a few more terms to tackle. What about data terminal equipment? Or DTE? Is that just a fancy way of saying computer?
That's a bit more specific than that.
Yeah.
DTE, or data terminal equipment, refers to any device that sits at the end of a data communications link. This could be a computer, a router, a printer, or any other device that generates or consumes data.
So basically, anything that connects to a network and exchanges data can be considered DTE.
Exactly. The term DTE is often used in contrast to DCE, or data circuit terminating equipment,
Okay.
which refers to devices that provide the connection to the network, such as modems or those CSU-DSUs we talked about earlier.
Okay, DTE, the data endpoints. Got it. What about default gateway? I think I've seen that term in my network settings before.
You probably have. The default gateway is the IP address of the router that a device uses to communicate with devices on other networks, including the internet. It's like the exit door from your local network to the wider world.
So if my computer wants to send data to a server on the internet, it first sends it to the default gateway, which then forwards it on to the correct destination.
Precisely. The default gateway is a critical setting for any device that needs to access the internet. Without it, your device wouldn't know how to get out of your local network.
Default gateway, the internet on-ramp. That makes a lot of sense. Okay, what about DMARC? That sounds like some kind of boundary marker.
You're right, it is. The DMARC, short for demarcation point, is the physical point where the responsibility for a telecommunications circuit changes from the service provider to the customer.
So it's like the property line between my network and the telecom company's network.
Exactly. The DMARC is usually located at the point where the service provider's cable enters your building. And it clearly defines who's responsible for maintaining and troubleshooting the network on either side of that point.
DMARC, the network property line. Okay, that's clear. Now let's move on to one that I'm sure everyone has heard of, DNS. I know it has something to do with websites, but how does it actually work?
DNS, or the domain name system, is one of those fundamental services on the internet. It translates human-readable domain names, like Google.com, into numerical IP addresses that computers use to communicate.
So when I type google.com into my web browser, DNS is what figures out the actual IP address of Google's server so my computer can connect to it.
Exactly. DNS acts like a giant phone book for the internet, mapping domain names to IP addresses. Without DNS, we'd have to remember long strings of numbers to access websites, which would be incredibly inconvenient.
DNS, the internet's phone book, makes perfect sense. What about domain itself? Is that just another word for website?
Not quite. In networking, a domain refers to a logical grouping of devices and users under a common administrative control. It's often associated with a particular organization or company.
So a company like Google might have its own domain that includes all of its servers, computers, and users.
Exactly. Domains are hierarchical, with top-level domains like .com.org and .net, and subdomains like google.com or wikipedia.org.
Okay.
Understanding domain structure is important for network management and security.
Domains, organizational kingdoms on the internet. Okay, let's move on to dynamic routing. Does that mean routes are constantly changing?
You got it. Dynamic routing allows routers to automatically learn and adjust to changes in the network topology. Unlike static routing, where routes are manually configured, dynamic routing protocols enable routers to exchange information and adapt to things like new connections, link failures, or congestion.
So dynamic routing is like having a self-driving car for your network traffic.
That's a great analogy. Dynamic routing is essential for large and complex networks
Okay.
that are constantly changing. It makes the network more resilient and efficient.
Dynamic routing, self-driving network traffic. I like it. What about encapsulation? Does that mean data packets are being wrapped up like presents?
You could say that. Encapsulation is the process of adding headers and trailers to data packets. As they move down through the layers of the OSI model, each layer adds its own specific information to the packet before passing it down to the next layer.
So it's like putting a letter in an envelope, then putting that envelope in a bigger envelope, and so on until it's ready to be mailed.
Exactly. Encapsulation ensures that data is properly formatted and addressed. For each stage of its journey across the network,
Okay.
each layer's header contains the information that layer needs to process the packet.
Encapsulation dressing data packets for success. Okay, that makes sense. Now, what about error detection? How do networks know if data has been corrupted during transmission?
Error detection mechanisms, like those checksums we discussed earlier, are used to verify the integrity of data packets during transmission. The sender includes a special code in the packet, and the receiver checks that code to make sure the data arrived intact.
So these mechanisms are like built-in proofreaders for data packets?
Precisely. If an error is detected, the receiving device can request a retransmission of the packet, ensuring that the data is delivered correctly.
Error detection. Quality control for data packets. Okay, let's tackle a few more terms before we wrap up. What about Ethernet? I know it's the most common type of network, but what makes it so special?
Ethernet is the most widely used LAN technology in the world because it's reliable, affordable, and relatively easy to implement. It defines the standards for physical cabling, signaling, and data framing at the data link layer.
So Ethernet is like the common language that devices on a local network use to communicate with each other.
Exactly. It's the foundation for most wired and wireless networks today.
Ethernet, the universal language of local networks. What about flow control? Does that mean networks have speed limits?
Flow control mechanisms are used to manage the rate of data transmission between two devices, preventing a faster sender from overwhelming a slower receiver.
So it's like a traffic calming measure for data packets, making sure everyone stays in sync and data isn't lost.
That's a good way to think about it. Flow control is especially important for ensuring reliable data transfer over slower or less reliable connections.
Flow control, keeping data traffic flowing smoothly. Okay, we're almost there. Just a couple more. What about frames? Are those like picture frames for data packets?
Frames are the basic units of data transmission at the data link layer. They encapsulate data packets and add header and trailer information, including source and destination MSC addresses, error detection codes, and other control information.
So frames are like the envelopes for data packets, providing the necessary addressing and labeling information for delivery on a local network?
Exactly. Understanding frame structure is crucial for troubleshooting network problems at the data link layer. By analyzing the information in the frame headers, you can gain insights into how data is moving across the network.
Frames data packet envelopes with extra instructions. Okay, last but not least, what about frequency? I know it has something to do with wireless signals, but what does it actually mean in a networking context?
Frequency is a measure of how often a signal oscillates per second, measured in hertz, or hertz. It's a fundamental concept in networking, especially for wireless communication.
So a higher frequency means a signal is oscillating faster. Is that why 5 gigahertz Wi-Fi is generally faster than 2.4 gigahertz Wi-Fi?
Precisely. Higher frequencies allow for faster data transmission rates, but they also have shorter ranges and are more susceptible to interference from physical obstacles.
Frequency, the heartbeat of wireless signals. Okay, I think we've officially decoded all the CCNA alphabet soup. That was quite a journey. You know, exploring all these concepts and terms really highlights just how complex and interconnected the world of networking is. It's amazing how all these different technologies work together seamlessly to allow us to communicate and share information globally. Thanks for guiding us through this intricate landscape. I feel much more confident in my understanding of these fundamental concepts now.
You're welcome. It's been a pleasure diving deep into these topics with you. And remember, the journey of learning never truly ends. The world of networking is constantly evolving, so stay curious, keep exploring, and who knows, maybe we'll uncover even more fascinating concepts in our next deep dive.
I'm already looking forward to it. To all our listeners out there, keep those brains buzzing and happy networking.